Welcome to part 3 of the onboarding series for servo and motion. In this session, we'll explore the critical role of servo amplifiers, the essential components that power and control servo motors. We'll break down how servo amplifiers work, their key design aspects, and the different types available, including all-in-one amplifiers, multi-axis systems, and DC bus configurations. You'll also gain insights into dynamic braking, energy efficiency, and the differences between servo amplifiers and inverters. Let's get started. Let's start with the most basic question. What is a servo amplifier? Servo amplifier, also known as servo drive, is an electronic device that provides power and control signals to servo motor. The servo amplifier receives control signals from the control system and converts them into precise power and current outputs that drive the servo motor. What is it used for then? The main function of a servo amplifier is to amplify and modulate the control signals to the servo motor based on the desired motion or position specified by the control system. It ensures that the servo motor accurately follows the commands and maintains the desired position, speed, and torque. A servo amplifier can generally be divided into two main circuits, power circuit and control circuit. The control circuit consists of both a virtual mathematical loop and a real loop. In simplified terms, when commands are sent from a controller, for example, a PLC, the servo amplifier processes these signals in the virtual loop. This virtual loop is then compared with the real feedback loop, and the difference is used to generate a properly modulated PWM signal to drive the servo motor. However, in this training session, we will focus primarily on the power circuit and its components. The power circuit naturally begins with the power supply that feeds the servo amplifier. This power supply can be either single-phase 230 VAC or three-phase 400 VAC, depending on the version of the servo amplifier. The AC voltage from the electrical grid first passes through a rectifier, which converts it into DC voltage. This DC voltage is then further smoothed by a capacitor, ensuring stable power delivery to the servo system. Another key component of the power circuit is the braking resistor. The role of the braking resistor is to convert electrical energy generated by the motor during deceleration into heat. This energy, known as regenerative energy, occurs in specific situations. For example, when controlling a vertical axis, the motor is not just driving a load, but is also resisting its movement, such as preventing a load from falling due to gravity. Since the load itself causes the motor to turn, the motor acts as a generator, producing voltage in its windings. To prevent damage to the servo amplifier's electronics from this returning voltage, braking resistors are used. Nearly all Mitsubishi electric servo amplifiers in the 100W to 7 kW power range come with a built-in braking resistor. For higher power amplifiers or situations where more regenerative energy is generated than the built-in resistor can dissipate, external braking resistors are used. These external resistors are connected to the P and C terminals of the servo amplifier. When an external resistor is used, the internal resistor is bypassed and all regenerative energy is dissipated through the external resistor. The last component of the power circuit in a typical servo amplifier is the inverter. The rectified voltage coming from the rectifier smoothing capacitor circuit is converted back into AC with a specific frequency, which is controlled by the control circuit. This modulation process is carried out using PWM pulse width modulation, utilizing IGBT insulated gate bipolar transistors to precisely regulate the motor's speed and torque. Each pair of transistors corresponds to a specific phase, U, VW, of the motor, supplying power to the respective motor windings. An additional component that can be considered part of the power circuit is the dynamic brake. This component is found exclusively in the servo drive portfolios of Asian manufacturers. Our standard amplifier portfolio, RJ, HS, as well as JE and JET, is always equipped with a dynamic brake. If, for technical reasons, this feature is not desired in an application, it is necessary to order a special version of the amplifier with the ED or RU suffix in the product name. Okay, so how does it work? The operation principle of the dynamic brake is very simple. When power is cut off from the IGBT output, for example, due to a power failure in the factory or activation of STO, safe torque off, The UV and W phases are automatically connected together. Since these phases are connected through a resistor, the spinning motor, which generates voltage, breaks itself. This happens because the generated voltage returns to the motor, creating an electromagnetic field in its coils, which effectively slows down the rotation until the motor comes to a complete stop. It is a braking function that is used at a power failure, servo amplifier malfunction, and immediate stop of the machine. Braking torque larger than the electromagnetic brake can be obtained by this function. However, it does not have a holding torque at stop. The Mitsubishi J5 servo amplifier has this function. The M servos, which have induction motors, do not have this function. The graph illustrates a significant difference between braking with and without a dynamic brake. Without it, the motor slows down gradually due to natural friction and load resistance, resulting in a longer coasting distance before coming to a stop. In contrast, with a dynamic brake, the UV and W phases are shorted through a resistor, causing the motor to generate regenerative voltage that feeds back into its own windings. This creates an electromagnetic braking force, actively decelerating the motor much faster. As shown in the graph, the dynamic brake significantly reduces stopping time and distance, making it essential for emergency stops, precise positioning, and improved safety by preventing uncontrolled motion during power loss. We can calculate the distance over which the load will come to a stop when using the dynamic brake by applying this simple formula. Please take a moment to study it carefully. This formula calculates the maximum coasting distance when using a dynamic brake, considering factors like speed, inertia, and braking response time. The initial speed of the machine directly affects how far it will travel before stopping, with higher speeds leading to longer stopping distances. The control system introduces a delay before braking takes effect, which includes relay switching time. Inertia also plays a key role. If the load inertia is significantly higher than the motor inertia, the stopping distance increases. The term that includes the inertia ratio accounts for how the total system inertia impacts braking performance. Lastly, the dynamic brake time constant determines how quickly the braking resistor dissipates energy, meaning a larger time constant results in slower braking and a longer stopping distance. In summary, heavier loads, higher speeds, and control system delays all contribute to extended stopping distances, while a lower inertia ratio and faster braking response improve braking efficiency. The operation of the dynamic brake is perfectly illustrated in the following video. On the left side, we have a vertical servo axis equipped with a dynamic brake, while on the right, there is an axis without one. We simulate a power loss on both axes and observe their behavior. The object placed under the right side axis, in this case, an egg, is almost immediately struck, causing it to break. Meanwhile, the axis with the dynamic brake moves much more slowly and eventually stops on the object without causing any damage. The dynamic brake is useful in almost any application, providing an additional layer of safety for the machine in case other systems fail, although it does not affect the SIL safety integrity level. A great example is vertical axis, where a brake release mechanism is almost always used. If this mechanism fails, the dynamic brake can slow down the load enough to prevent damage to the application. Another excellent application is horizontal linear axis with heavy loads. Due to inertia, a moving axis will not stop immediately through friction alone, coasting. In many cases, this leads to machine components getting damaged as the load literally crashes into them. The dynamic brake helps prevent such impacts by significantly reducing the stopping distance. Additionally, the dynamic brake can also be used with vertically mounted linear motors. Due to their design, if a power failure occurs or STO is activated, the motor, whose coil is no longer powered, will immediately drop due to gravity. Not every linear motor manufacturer includes a built-in brake release mechanism, and in fact, this feature is quite rare. When designing a machine, there are a few options to address this issue. One option is to accept the falling motion and design the application in a way that prevents damage to any components. Another is to install an additional brake on the linear guides, either pneumatic or electric. However, a more effective solution is to use a servo amplifier with a dynamic brake, which will slow down the axis before it hits a stopper or any other machine component, preventing damage. Despite its undeniable advantages, there are rare situations where a dynamic brake may not be recommended, which is why servo amplifiers are also available without it. If the application's moment of inertia is significantly higher than the servo motor's inertia and power is lost while the motor is running at high speed, the dynamic braking system could be damaged. This typically happens when the resistor connecting the phases burns out due to excessive energy dissipation, potentially leading to servo amplifier failure and the need for repairs. This is why proper drive selection is crucial, ensuring that the motor and braking system can handle the application's inertia without risking component damage. You've now learned how the power circuit of a servo amplifier is constructed, and you've likely noticed that it is very similar, if not identical, to the circuits used in Mitsubishi electric frequency inverters. So, what sets a frequency inverter, such as the FRS series, apart from a servo amplifier? The key difference lies in the highly advanced control system built into the servo amplifier. Unlike a standard frequency inverter, a servo amplifier is specifically designed for precise motion control and dynamic response. Additionally, a servo system always includes feedback from the motor's encoder, allowing for real-time adjustments in position, speed, and torque, something a standard inverter does not provide. What types of amplifiers do we offer? All-in-one single-axis amplifiers are built in the way we have discussed so far. The power circuit and control circuit are housed in a single compact unit, with each amplifier capable of controlling only one servo motor. These servo amplifiers are ideal for decentralized electrical cabinet systems and centralized cabinet systems with a small number of axes or low-power servo axes. Typically, in our portfolio, these amplifiers range in power from 100 watts to 25 kilowatts. This power capacity directly corresponds to the motors they can drive, with the smallest 100 watts amplifier matching the smallest compatible motor. All-in-one multi-axis amplifiers have a similar design to the single-axis versions, but they integrate multiple control circuits and current output terminals, either 2 or 3, depending on the version, within a single housing. This allows one amplifier to control up to 3 servo motors. These amplifiers are primarily used in decentralized cabinet systems, but they are also suitable for centralized cabinets due to their compact size, which can reduce control cabinet space by 40 to 50%. They are also ideal for Cartesian manipulators, as a single amplifier can control the entire manipulator. Available power capacities are directly related to the motors they can drive, with the smallest multi-axis amplifier offering 200 watts, sized for the smallest compatible motors. Additionally, this type of amplifier is highly energy efficient. Since all servo axes operate on a shared DC bus, they can exchange regenerative energy during operation. For example, when one servo motor breaks, another can use the recovered energy for acceleration, reducing overall energy consumption by up to 23%. Common DC BUS systems consist of 2 main components: a converter that contains the rectifier, and drive units responsible for controlling the servo motors. This type of system minimizes the space required in the control cabinet while also offering high energy efficiency, similar to multi-axis all-in-one amplifiers. In these systems, servo axes share a common DC bus, allowing them to exchange regenerative energy, which can reduce overall energy consumption by up to 50% in suitable applications. Common DC BUS systems are always used in centralized control cabinets with a large number of servo axes. Available power capacities range from 0.05 to 7 kilowatts per axis, depending on the motor size and application. There are own and 2-axis amplifier types covering 17 kilowatts, as well as 3-axis amplifier types available in 1 kilowatt and 2 kilowatts versions. While it is technically possible to connect a 50-GA motor, it is not cost-effective. A single system can control up to 69 servo motors within just 1.5 meters of cabinet width, making it significantly more compact than all-in-one systems. What exactly is the difference between an all-in-one amplifier and a common DC bus system? The converter. As mentioned earlier, all-in-one amplifiers feature a built-in power and control circuit. This means that every component needed to control the servo axis is housed in a single enclosure. Common DC bus systems operate differently. The first element of the system is a converter that contains a rectifier and a capacitor bank. The converter is then connected to so-called drive units via a common DC bus, supplying them with DC voltage. The task of the drive units is to properly modulate voltage and current in correspondence with their control circuit. As previously mentioned, this setup allows for space savings in the control cabinet, but also enables the exchange of regenerative energy between the drive units. This energy, generated during motor braking, is stored in the capacitors inside the converter and then distributed as needed to the servo axis. If the braking energy exceeds the system's storage capacity, the servo converter can return the excess energy back to the power grid. In multi-axis systems, no braking resistor is needed. Energy is stored in the capacitor and shared between drives. This enables significant energy savings, especially when machine motion patterns are synchronized so that one axis decelerates while another accelerates. To finish the video, let's have a look at the summary of each of the discussed products, starting with all-in-one. Moving to multi-axis all-in-one. And finishing with common deep bus. Congratulations on completing part 3 of the onboarding series for servo and motion. You now have a solid understanding of servo amplifiers, their design principles, and how they impact system performance and efficiency. We hope this session has been both informative and engaging. Stay tuned for part 4, where we'll continue diving deeper into the world of servo and motion technology. See you there!